All right, let's see. Let's take a moment here to make sure I'm live, make sure the audio is working. 1, 2, 3, 4, 5. What are we doing here?
Hello,
5.
hello, hello.
What are we doing here?
Hello,
5.
hello, hello.
All right, pop the chat out, and we'll start with this next question. So this says, smallest integer divisible by k. Let's see what this one is. I don't know. I don't actually know what this one is. We'll see. Let me see my. I just refresh this, that way it's updated. Okay, given a positive integer k, you need to find the length of the smallest positive integer n. How am I doing? Okay. Smallest positive integer n, such that n is divisible by k, and n only contains the digit 1. Return the length of n. If there is no such n, return -1. A may not fit in a 64-bit signed integer. Whoa. Whoa. Okay. It's got a very low success rate. Okay. K could be between 1 and 100,000. Okay, so length of the smallest positive integer n, such that n is divisible by k, and n only contains the digit 1. Okay. Length, so the number of digits in n. Oh, interesting. No such positive integer n divisible by 2. This one is 3. I think this is kind of straightforward. Basically, to be divisible by k, you take modulo k. And n could be, n itself may not fit in a 64-bit signed integer, but n the length of n can fit in a 64-bit integer, and k could be up to 100,000. Interesting. The smallest. Length of the smallest. So yeah, basically, I don't think this is too hard. I think this is kind of straightforward. What you're going to do is each digit is some power, right? You're basically going to take things modulo k, right? Take things modulo k. And you're going to add things modulo k until you have 0, right? The sum of this stuff modulo k is 0. And the sum, yeah, it can be done. This can be done efficiently in 100,000 operations. It's fine. Basically, so k fits is all you need to know. You don't need to know that. Yeah. So this isn't too bad. This isn't too bad. This is like a prefix sum type of a thing. All right. Count starts off at 0. The way we're going to do this is a prefix equals 0. It actually starts off at 1, right? The first value, count is 1, prefix is 1, k is 1, I think. K is always at least 1. We're going to say while prefix is not equal to 0. Return count prefix modulo k, 1 mod k. While prefix is not equal to 0, we're going to say, all right, we're going to add to prefix a certain number and then take that modulo k. That number is going to be a power of 10. Actually, it's literally just going to be a power of 10. Yeah. And just say current equals 1 mod k. Also, current, we're going to say increment the count. We're going to say current times equals 10, current mod equals k. and then add this value to, what is going on? Add this value to, something like this. It's maybe not, the kids are playing or something. Hopefully also this doesn't, okay. What is, oh, wait a second. Oh, there's no such, oh, okay, I made a mistake here. Oh, the TLE is a -1. So it could be the case that this is never divisible by 2, or it can never be divided, but yeah, it's never, this modulo can never happen. I think the count is bounded by k. I think so. I mean, we could just say and count is less than k. Let's return count is less than k, then return count, otherwise return -1. I mean, we could do that too. It's I don't think that's quite right. Oh, okay. Maybe I got this wrong. I don't know. Let's do a bunch of other things. All right, I don't know. Just doing this like kind of brute force, or a straightforward brute force solution. I don't know if this is the right way to do this. I don't know, is basically there's some assumptions I'm making here. I think they're correct, but it's not obvious. So one of the assumptions is if the count is how many things are being added. Like we're adding things repeatedly to the the modulo value, right? Each time we're just adding another 1 or 10 10 raised to some power modulo k, right? We're just adding that repeatedly to our prefix. The problem is that it could be the case that, yeah, this is never actually, this number is never actually gets to 0. It's never actually divisible by 0. And the question is, how do I know when that's the case, like efficiently? How can I efficiently determine that it'll never be the case, no matter how many times we add these values, that we're just never going to get down to 0? And I think the way to figure that out is if there is a cycle, right? And there's a cycle, it's guaranteed if the count is greater than or equal to k, and we still haven't seen 0, then we've gone through at least, so there are k values in mod k, there are k possibilities mod k, right, 0 to k minus 1. If we've seen k or more, then we've got to stop, right? Because we've reached a cycle of some kind. So yeah, it's guaranteed that if the count is greater than or equal to k, then return -1. I think Now, there's something else going on here, though, where the count could be k in some cases. Like this one. And this one. Which is confusing. So, yeah, I got to think about that too. If we've exceeded k, then we could actually reach every single value of every possibility, which is k. Yeah. So that's really what it is. So it's going to be okay. I think I have it right. So confusing. I think I have it right with that condition. Is that basically if you've reached every value of k, every possible value of k, and you still haven't gotten 0, then really this is just if you've repeated a value. It's kind of what it comes down to. Yeah. If you've repeated one of these current values. Well, I don't know if it's, pigeonhole principle works here, but yeah, you could reach every value of k. Yeah, what's confusing about it is that it's not every value of k. It's that if you're able to reach k and you haven't stopped, that means you're in some kind of a loop. That's what it is. That's I realize it's confusing. There's a better way to do this, I'm sure, but let's go for this. I think this is correct, even though it's not really the best. It works. It's not the best. It works. It's a little bit confusing as to why. I'm going to submit it a few more times. I don't think this needs to be perfect, though. Like, this is probably good enough. Has something to do with the pigeonhole principle and cycles. You could use some memory to optimize this, I think. So what you could do, if you wanted to, is could use an unordered map or unordered set. And then let's just say scene. And we're going to say and right, we haven't seen this prefix yet, right? What we're going to do is insert the prefix. But basically, if you repeat a prefix, then it's a cycle. Then you're in some kind of a cycle. Ooh. It's pretty quick, actually. It repeats. So no. No. Is it that you repeat a current value or you repeat a prefix? I think it's okay to repeat prefixes and current values. How do you know you're in a cycle? How does that happen? I think when you repeat current values, actually, is what it is. Then you're in a cycle. Nope. All of these, same thing. They all exit so quickly. Oh, no, go back. I think it, yeah, okay, never mind. Oh boy. Okay, maybe I did have the right idea. When you repeat a prefix, right, then that's a cycle. In both of these cases, we return -1, otherwise return count. Okay, I don't know if this is still correct. I'm assuming it's still correct. I could try it, see what happens. Oh, yeah, it's correct, but now it's slower. The other one was faster. Yeah, it doesn't really matter. The benefit of doing fewer operations doesn't really outweigh the hashing of the integers here, which is weird, quite frankly. But yeah, it seems to be. It's weird that would be the case, but that's how it is. It's faster to just do a lot of extra operations because it's being hashed, right? It's being hashed. There we go, 100%. Hail victory. Got 100%. Beautiful. That's what I like to see. Yeah, that one I spent some time on. I spent a little more time on the previous question because it was a binary search thing, but this is okay. This is what it is. Yeah, a little bit of a math theory type of thing. All right, let's go to the next one. So, all right, so I'm gonna go ahead and stop the stream there. I want to take a break. It's like 1:45. Maybe I'll go till like 3. I'll go another hour and 15 minutes. Go for another hour and 15 minutes. I'll stop here. Try to get this clear screenshot, and then yeah, I'll stop here, and then I'll continue with. I'll keep going till 3. I'm going to stop the stream and restart it.